In this section, we discuss a term known as molarity. And molarity is defined as moles of solute per liter of solution. So in this example, we have to calculate the molarity of a solution made by putting 15.5 grams of sodium chloride into a beaker and adding water to make 1.5 liters of NaCl solution. Notice, I said when we make solutions, if you've looked from your previous slide, then you know that first you have to take your sample, your solute of NaCl, add it to your volumetric flask here, and then you fill up your water to the mark. So this would be, if this was a 1.5 liter flask, you put your 15.5 grams of NaCl and then fill it up here. So you have 1,000 or 1.50 liters of sodium chloride solution total with water and solute. That's a very, very important concept when we're talking about molarity. So here's molarity being defined as the moles of solute, which is salt in this case, over the liters of solution. Key point is solution. So do we have the moles of solute? No, we have the grams, so we have to convert that into moles. But that should be very easy for us by now. 15.5 grams of NaCl. Since grams is on the top, I'm going to put grams on the bottom and moles is on the top. How do I go from grams to moles? This should be a very big hint for you whenever you see grams to moles or moles to grams. You have to use the molar mass of sodium chloride. So for every 1 mole, I have 58.44 grams of sodium chloride. This should then give me 0.2652 moles of sodium chloride. And I'm just going to put an underline to know how many significant figures this is. So now that I have this, I can go ahead and plug this in. 0.2652 moles of NaCl, which is my solute, over liter of solution. And this is already in liters, so 1.50 liters. And so this gives me a solution that has 1.77 molarity. And this is a uppercase M. Okay, now you go ahead and give this a try and replay the video to see if you got the correct answer. Let's calculate the molarity of the solution made by putting 55.8 grams of sodium nitrate into a beaker and diluting to 2.5 liters. Okay, so remember what molarity is. The definition of molarity is moles of solute over liter of solution. Okay, and so here we need the moles of solute, and the solute is sodium nitrate, but we're given grams. So the first thing that we want to do is convert our grams into moles. So 55.8 grams of sodium nitrate. We want to go from grams. I put grams on the bottom because here the grams is on the top. Grams of sodium nitrate over moles. Okay, and for every 1 mole, the molar mass is 85.00 grams. And so we end up with 0.65647 moles of NaNO3, or sodium nitrate. Now I'm ready to plug it into here. So 0.65647. Of course, I'm going to underline this so I know when to stop for significant figures, but I don't want to just round yet, so to avoid round-off error. and I got 2.5 liters of solution. And this is moles of solute, which happens to be sodium nitrate. And so my molarity should be 0.263 molar. Okay, we're going to learn how to use molarity as a conversion factor, just like we've previously learned to use density as a conversion factor between mass and volume. Now we can use molarity as a conversion factor between moles of solute over liters of solution. Okay, so if I have a 0.758 molar solution of sucrose, that means what? I have 0.758 moles of sucrose for every 1 liter of solution. Do you see how that's a conversion factor? Let's see how we apply that. If I have, I want to know how many grams of sucrose are contained in 1.72 liters of 0.758 molar solution. So my starting value is 1.72 liters of solution. Okay? And then, now I can use this conversion factor. For every 1 liter of solution, I have 0.758 moles of sucrose, or I'm going to write the name for it. The chemical compound for that is C12H22 and O11. Okay? And so I don't want to stop there because I'm being asked how many grams of sucrose do I need. Well, I have moles, so in order to go from moles to grams, what do I need? I need the molar mass of sucrose. That's why I gave you the molecular formula for that. And that is 342.34 grams of sucrose. So remember that sucrose and C12H22O11 are the same exact thing. So you see how liters cancel, moles cancel, and I'm left with grams of sucrose. This should give you 446 grams of sucrose. And I read the question to make sure I've answered it. How many grams of sucrose are contained in 1.72 liters of 0.758 molar solution? I think this is supposed to be solution. Sucrose solution. Yes. Okay. Go ahead and give this a try and replay the video to see if you have the correct answer. How much of a 0.225 molar KCl solution contains 55.8 grams of KCl? Okay, now we want to always start with what we're given, right? But we recognize that the 0.225 molar means I have 0.225 moles of KCl or solute for every 1 liter of solution. So here I'm given the mass of KCl. So if I have 55.8 grams of KCl, or potassium chloride, I want to be able to convert to liters volume, because I want to know how much of a 0.225 KCl solution contains 55.8 grams of KCl. The only thing that I can't go directly from grams to liters, I have to use this conversion factor. That's how molarity becomes my conversion factor. But I can't use it just yet because my molarity is given in moles per liter. So the first thing that I want to do is convert my grams to moles. And this is KCl. For every 1 mole of KCl, I have 74.55 grams. And now I'm ready because I have moles of KCl I can now go from moles to liters. So it seems that I have moles of KCl here, and I'm going to put liters of solution up there. And for every 1 liter, I have 0.225 moles of KCl. And so you see the grams cancel, the moles cancel, and I'm left with liters of solution. This should give me 3.33 liters of solution. And I look to see if I've answered my question. Yes, how much of a 0.225 molar KCl solution contains 55.8 grams? So this is the correct answer. Now we're going to add one more concept to molarity. We know that when we report the molarity of a molecular compound, that reflects the concentration of the solute as it actually exists in solution. So sucrose or glucose, let's say glucose is C6H12O6. This is a molecular compound. Why? Because they're all nonmetals in there. So molecular compounds do not break up in solution. And so if I have 1.5 molar of glucose in solution, it'll stay as 1.5 molar glucose in solution. I have 1 mole of glucose for every 1 liter of solution. However, if I have an ionic compound, the ionic compound breaks up in its constituent cation or anion. So if I have calcium chloride, it's going to break up into calcium ion and the chloride ion. But notice, for every 1 calcium ion, I have 2 chlorides. So if I had a solution that was 1.0 molar of calcium chloride, what I really have is 1 mole of calcium ion per liter of solution, but I have 2 moles of chlorine ion per liter of solution. So we have to take the stoichiometry into effect. All right, let's apply this to this example. I first recognize this is an ionic equation. Why? Because it's a metal and a nonmetal. Okay, and so this is the sodium ion, and this is the phosphate ion, right? And it has a -3 charge. That's why I made you learn all your polyatomic ions, because they're very useful. So when I break up my sodium phosphate, I'm going to get sodium and the phosphate, the sodium cation and the phosphate anion. But notice I have 3 sodiums for every 1 phosphate in order to get this balanced formula. That means if I have 1.50 molar of this, then when it breaks up, I should have 3 times that much for the sodium ion and 1 times 1.5 here. So now I have 4.5 molar of the sodium ion, and notice I put brackets around the sodium cation to indicate the concentration. So if you see brackets around something, that means the concentration of the sodium cation. And here my potassium anion is still going to be 1.5 molar. Okay. Now let's go ahead and try another example, and you try to figure this one out for me. Determine the molar concentration of the calcium ion and the chlorine ion in a 0.75 molar calcium chloride solution. Okay, so I already showed you here how that works. Let's see, if we have calcium chloride, it's going to break up into the calcium cation and the chlorine anion. But notice we need 2 moles of chlorine for every 1 mole of calcium. If this is 0.75 molar, then this is, since it has a 1, it has to be 1 times 0.75, and this has to be 2 times 0.75. So the concentration of the calcium ion is 0.75 molar, and the concentration of the chlorine ion is going to be 1.5 molar.